Welcome to week 6 of IS50B, a extra special lecture. Hope you guys don't mind kind of reviewing some of the IS50A stuff. It's just kind of working out that way. I'm giving you a little bit more advanced versions of the first semester stuff. It should be good for you to go over making materials again and stuff like that, right? Stover, Krente, you guys all right doing a dynamic?
Yeah, another refresher.
All right, yeah, it's good for me too, because I'm not really an art person, so having the chance to do some art is always fun for me. Cool. All right, so what we're going to talk about today is some computational geometry again, and the topic is called Voronoi. And what a Voronoi diagram is basically identifying the areas that are closer to one point than to another point. And here you can see they're colored, right? So what they did was they randomly scattered these seed points, which could be cities, they could be, cell nuclei, whatever. They scattered them across the 2D grid here, and then they colored in the areas that are closer to one seed than another. Does that make sense? Stover, Krente?
Yes.
Yes.
So they're
Okay.
like, if there was a group of them, they made groups almost.
Yeah. So basically, what I might ask is, like, if I was here, which one of these points am I closer to than any of the other ones? Okay. So, like, let's say that I'm writing a video game, and there's each one of these points is like a stables somewhere in the world, and I turn my horse loose, and the horse says, "I want to run to the nearest stables." Well, if you had a Voronoi diagram for the world pre-computed, it would just be like, "Oh, go to the pink stables," and then the horse would pathfind over to that one. Basically, for every point in the world, you can say which one of these points here, these seed points, am I closer to than any others. So if I'm up here, I'm still closer to the pink stable. If I'm over here, I'm still closer to the pink stable than any of the other ones. And these things are actually surprisingly useful. There's a lot of very interesting applications for Voronoi regions, and you can use them in a lot of ways. For example, you could scatter some random points and turn these into cobblestones, right? So you just take these kind of polygons, and then you make you kind of round them off a little bit, and you can have like an irregular cobblestone street where you don't have like a repeating grid texture over and over again, but rather it just sort of dynamically generates where all of the cobblestones are, and it just kind of looks good. People have used these for generating random fantasy maps and things like that, where each one of these might represent like a chunk of land, and this might be water, and so basically it might make islands and rivers and mountains and things like that. So they're actually used in a lot of different ways. Hitbox area for the point, kind of, yeah. It's like if I shoot this point here, then tell me which one of these points did I hit closer to than any of the other ones. And so the larger version is below. Yeah, not very helpful. And so this is Manhattan distance, where going north, you can't go diagonally, right? So these look a little weird if you're doing Manhattan distance. You can only go north, south, east, and west, right? And random set of points in a 3D box. In general, a cross section of a 3D Voronoi tessellation. It's not a 2D Voronoi tessellation. So these are 3D. It's a cross section of a 3D Voronoi. Okay, so you can use them. Yeah, you can make a honeycomb or something like that. You can use them, and Oh, that's cool. That looks neat. That shows you kind of how, yeah, it kind of shows you kind of how one of the algorithms works. We're not going to be doing that algorithm. Yeah, so you can use them to answer nearest neighbor queries, like, which city am I closest to, right? And the nearest hospital or the nearest thing. In computer graphics, I don't know if they have an example on here, but like I said, they're used in a lot of different ways. They're related to a concept called a Delaunay triangulation, where you given a set of points, you triangulize it in such a way that no point is within the circle of another point, basically. So because if you have a bunch of points like this, like it's possible to come up with like really ugly looking triangles. Like you go 1, 2, 3, and have these really long, narrow, thin triangles. And so the Delaunay triangulation basically says no point could be within the circle of another point. Then you would pick that one instead from the edge. And so it's actually the same application. The Voronoi and the Delaunay triangulation are actually complements to each other. It's actually the same, basically the same algorithm. And connecting the centers of them produces the Voronoi. Yeah. So these things have all sorts of. It seems like it should be a circle, right? But when you have two different points, then it ends up drawing like a straight line between the two, right? Because that's you're going to be near on one side or near on the other. It's like the intersection of two circles, kind of. And and so the Delaunay triangulation keeps you from having like really long and narrow triangles. So they generated 100 random points, and they triangularized it, and they created a mesh from it. So this is a triangular mesh, and you can see that you've probably seen things like this in in Unreal Engine and things like that, where they sort of generate these random things. So.
Would this be something like a convex hull algorithm, except you don't make the convex hull, and like instead of ignoring the points on the inside, you draw a line in between it?
Yeah, actually, this the outer thing here is a convex hull, I think, but a triangularization will also split up like concave holes and things like that. So it creates kind of a if you have a concave hole, when you triangularize it, it splits it into multiple convex holes. So, okay. So let's talk about. It's kind of cool. So let's talk about how to implement this, because that's going to be your assignment over the next week. So, chcd Voronoi reference. So your assignment is to randomly scatter points across the map, and then color them. Color the world based on which points are closer to which cities. Okay. So I'm doing, I think, 23 cities, something like that. And you can see every time it picks a random color for each city, and you get these kind of polygonal regions as the result of it. Now, one of the nice things about the way that we're doing this assignment is that you don't have to handle just arbitrary points in space, which has a different algorithm for it. This algorithm is actually pretty damn simple. All you do is just, for every point on the world, you see which city is closer. It's a very inefficient algorithm. That makes sense, Stover? Corrente? So, For this point right here, you do a hypot, right? Hypot to here, hypot to here, hypot to here, hypot to here. See which city it's closer to. And if it's closer to K than it is to any of the other ones, then you write down, okay, I'm a member of country K. Then after you've colored the whole thing in, you count to see which country is the biggest. So it turns out Hong Kong is the biggest city with 420 tiles. So this is just a tile-based system. For every tile, you just do a Euclidean distance, the Pythagorean theorem, right, to each city. See which one's closest, and then write down, okay, this tile is within the limits of city 15. This tile is within the limits of city 15. This tile is within the limits of city 12. Yep.
So we have all the cities, and then we have the tiles. And then so we start from the center of the city and go out, and no?
No. Just for every tile. You could, if you wanted, you could do a radius search where you're going out one from each city and then 2 out from each city. You could do that. You could do it that way. That'd be fun. That'd be interesting. I, however, did it the lazy Kearney way, which was just to say for every tile in the world, figure out who the nearest city is, and then write that down. And so this whole map here is just a 2D array of integers. And the integer is which city is my parent.
See.
And I've got 23 cities, and so yeah. So every tile just has an owner, and the content is whether or not it's got that letter there, like the letter C, or nothing. So it's just each tile just has an integer, and then my city class randomly generates a color from 0 to 255. All of the cities are named Fresno by default. You might want to fix that or something. Probably, I think it's in the instructions. You have to fix it. Thankfully, we could be inefficient and just check against every point. Yeah, and the nice thing is that the nice thing in a lot of applications, you really don't need it to be that fast. This is not a large world. I mean, who cares, right? Who cares? You're going to be doing a lot of lookups on it oftentimes, but you only have to generate it once, and so if you want to be inefficient, it's fine. So, so the first city is going to be called Fresno 1, then there's Fresno 2, Fresno 3, Fresno 4. I use a static member variable. So Stover, Krente, do you know what a static member variable is?
It is modifiable outside the class? Inside the class?
It is shared amongst all the instances of that class. So every class,
a different keyword.
a static variable, a static inline variable means that every instance of this class shares the same integer. And so every instance, so you can tell, if you can ask every city, hey, what is your count? They'll all give you the same number. And so you can actually find out how many times this class has been instantiated, which is kind of nice. Kind of like a global variable for the class. That's exactly it. Yeah, it is a global variable just for that class. It's only visible within that scope. And it's public, so actually main could query it too. How many times have I made a city? And it'll tell you. So that's kind of cool. Every city has a name. Every city has an RGB value, and it's got a row and a column that its location. Okay. We then have a global list of all the cities in the world, and then basically you're gonna say for every somewhere in here you're gonna do it right. So for every tile in the world, you're gonna set the owner of that tile. You're gonna set the owner of the tile to be the nearest city. And then when you're done doing that algorithm, you're gonna call print world, and print world will draw that map. Okay. Makes sense? Do you know how to draw colors and things like that on the map? Find out. Inside of the module section on Canvas, I have a I have 2 short videos. One is an introduction to ReadLib, which I'm sure you're both familiar with by now. And the other one is an introduction to ColorsLib, which is how you can move the cursor around on the screen, how you can set the color, you can set the background color, and things like that. So, boom, this clears the screen. This sets all the colors back to default. This moves the cursor to row 0, column 0. And so basically what you're going to do is you're basically going to move the cursor. Actually, as you see out, the cursor moves to the right. So you just start with the cursor at the top right, and you iterate across the 2D world, which is this thing here. And you set the color, the background color, usually, to the R, the G, and the B values of the city. And print space. So if you do this, that will echo a space. It will draw nothing, but the background color will be set, in this case, to 100, 200, 100. You would set it to the color of the city, the R, the G, the B value of the city. And so you just call set background color, you print a space, you go to the next tile, set the background color to that tile's owner, print a space. That's all it is. The only time you don't print a space is when it's the actual capital city, and then you draw the character instead, that thing. Do you have to worry about moving it to a new row? I would, because I don't trust Putty to wrap around properly. So when I get to the end of a row, I call move cursor. I would do like a move cursor to row 1, column 0, and then do the next row. Yeah. I do that just in case, it doesn't wrap properly or something. You can try not doing it, but like basically at the start of each row, I move the cursor to the first column on that row, print out all the colors, and go through it. And so that's your assignment. So let's see what else there needs to do here. Yeah, come up with better names. You need to have a better name. Have you seen this before? Auto square brackets and stuff. Yeah. Krente?
I think so. I was just going to say, does that just make a 2D array?
It doesn't. This is actually something that was introduced in C++ 17. So C++ 17 has the ability to automatically unpack a struct. So get terminal size returns, I think, either a pair or a tuple. Whatever, it's just a plain old data structure. And so C++ 17 allows you to automatically unpack it into a regular variable. And so this creates 2 variables, one named rows, one named columns of type, I think, int. I think get terminal size returns 2 ints, a pair of ints. And so this just makes it's a way of returning 2 values from a function. Okay? So this is returning 2 ints, the rows and the columns on the screen from, it's a way to split a tuple. Yeah. Mm-hmm. But you can only do it when the variables are made. That's kind of the only annoying thing about it. If you call get terminal size again, you can't. It only works when the variables are made. And it essentially, you're getting a tuple back, and it creates you are the first part of it, and you are the second part of it, and it grabs the data. And if you didn't do that, you would just grab a struct and then split the struct up into 2 variables. It just saves you a line of code. That's all. We then resize the world to have a number of rows equal to the number of rows on the screen. We resize the number of columns to be the number of columns on the screen. And so that makes a 2D array right there. Hopefully they don't change the size of the terminal afterwards, right? This will only work. It only works if you keep your putty the same size. If you resize your putty, it'll break everything because this code doesn't call get terminal size again. Yeah, and so you're going to end up doing something like this. You're going to say the world at row 10, column 30 has an owner of city 12. Okay, so that's just the index into the city's vector. After you've run this algorithm on every tile in the city, you've set all the owners, then you call print world. Print world prints the thing, and you're done. Oh yeah, there's one other thing. So the last thing to do is to count which city is the biggest. So go through, count how many are owned by city 1, how many are owned by city 2, how many are owned by city 3. Whichever one's the biggest, that's the winner. Fresno 1 wins or whatever. Okay. So Voronoi is a Voronoi. It's Voronoi. There's an O missing in there. It's a very useful algorithm, and the algorithm should not be too complicated for you, I think, right? Like, do you understand the basic algorithm? Like, do you need me to draw it out? Like, do you want me to open up OneNote and kind of sketch it out for you? How the algorithm works?
I wouldn't mind a sketch.
All right. Let's do this. Okay. Mm-hmm. Okay, so let's say that you've got a city here, a city here, and a city here. You're going to start, and you got a grid, right? Okay, so let's say you start here. You're at row 0, column 0. This city here is at row 3, column 0, 1, 2, 3, 4, 5, 6. So this city here, let's colorize it, I guess. The red city is at row 3, column 6. The galaxy city is at 1, 2, 3, 4, 5, 6. 6, 6. And the purple city is at 2, 6. So you start on the first tile, and you do the Hypot function, right? You check the Hypot, the Pythagorean distance, to the 3 cities. This can be done with Hypot cities x minus my x, or column, I guess, however you want to call it, and cities y minus my y. So my, what is that, row. So the city's row minus my row, the city's column minus my column, however you want to do it. And so let's say this one is going to be, was it 4 squared plus 36, 40, square root of 40. So this one is the square root of 40 away. This one here is the square root of 72 away. And this one here is 9 plus 36 is the square root of 45 away. So this city here is the closest, and so we write down the owner of this tile is purple. So you write down, if this is index 0, you write down it's index 0, whatever. Then you move on to the next tile, the next tile, the next tile, the next tile, the next tile. And each one of these is going to be, like when you get here, it's going to check the Hypot to here, the Hypot to here, and the Hypot to here. It's going to be closest to red, so it's going to, my owner is red. You just go down the row and just you do the Hypot function over and over again. Make sense? And at the end of the day, you're going to get something that, has the purple areas over here, the red areas over here, and the galaxy areas over here. Make sense?
Makes sense.
Now, there is one thing that you need to watch out for. And that is subtracting rows and columns. Do you see why it says? Do you see where it says "Hi, happy face, shrug emoji"? That's because the fact that what is size t? It's an unsigned 64-bit integer. if you are an unsigned integer and you subtract, like if you subtract one row from another row, and you get a negative number, what do you get? Like if you do the subtraction here, right? If this is a size t and this is a size t, unsigned, was it? Yeah. So the location is a size t, right? And that location is a size t. What do you get? Yeah, you get underflow. So 3 minus 5 works. This works just fine if they're signed integers. If they're unsigned integers, 3 minus 5 is equal to some amazingly large number. And then your Hypot gets all screwed up. Okay? So that's why I have this little thing here, because by the time you've debugged it and tracked it down, you're like, oh, it's just because it's an unsigned integer. First thing I would do in your case is I would change it to be an int. All the x's, all the y's, just use ints. You know, size t's are great, but anytime you do subtraction between two unsigned integers, it's bad. It's bad. Homework. IS50B. Voronoi. Misspelled, of course. Okay. That's the one thing that'll get you. So, first thing I would do before you forget is to eliminate all unsigned integers. I take that back. The colors need to be unsigned 8-bit. But the position, in the rows and columns, anything that refers to a row and column, just use a regular integer, not a size t. Okay? Because then because you're going to be subtracting one row from another to get the distance. And you get weird results. Because the code works on one side, it works to the right, but it doesn't work to the left. You know, you're just kind of like, what? You know, so that's it. That's our class for today. Any questions? Okay, I'll see you guys next week. And class on Thursday is going to be online. All right. Peace out.